Good morning, students. This is the fourth lecture or fifth lecture on the module 3, that is chapter 3 of boundary layer theory and its applications. So lecture 4 states that the boundary layer, the topic for this lecture is boundary layer on a flat plate. That is and ZPG. ZPG. So ZPG stands for the zero pressure gradient boundary layer. Now, the boundary layer on a flat plate, with or without pressure gradient, the objectives are that we are going to study the velocity profile or derive the velocity profile on boundary layer on a flat plate with or without pressure gradient. Now, the solution, so in this today's lecture, I will be stressing more on how to achieve or derive the solution of this boundary layer through the differential approach. Now there are two approaches. One of them approaches is called the approximate analysis, and the other, or which is basically based on the integral approach, and the other is on the pressure gradient, and is the differential approach. Now the second objective for the today's class is that we will learn the Blasius boundary layer solution. Now, now since we are starting the part, so let us first revise the boundary layer equations, which is the steady flow over a flat plate surface. So continuity equation is the normal continuity equation, that is del u by del x plus del v by del y. V velocity is given by minus times of del u by del x into del u by dy. The x momentum equation is given by the x part, given like this. Since it's steady, so time variation is not there. So this is del u by del x plus v del u by del y plus a is equal to u infinity du infinity by dx. So this u infinity is the velocity which is outside the boundary layer, and we will be evaluating this from the help of viscosity. So, so this slide shows the boundary condition and the governing equations for the boundary layer governing equations on a flat plate. So as you can see that at the flat plate, which is y is equal to 0, the velocities are no slip, due to no slip, that is u and v both are 0 for at all x stations. At y is equals to infinity, the u tends to u infinity, and del u by del n, and for all derivatives of u velocity vanish at when you go outside the boundary layer, that is at y is equal to infinity for all stations. Now the solution of the boundary layer equations is something like this, that we are going to discuss the solution. So let us, so this is the geometry on which we are hinting the solution. So this, so u infinity comes from the outside of the boundary layer. So there is no boundary layer right now at the left most corner part, and this flow u infinity interacts with the wall, and the boundary layer starts to grow. So as you already know, this portion which is below the boundary layer, this line, blue line, is affected by the viscosity, and this is the boundary layer, and the portion which is outside the boundary layer is where it is not affected by the viscosity. Now, since so this is the velocity profile u, this is the velocity profile which we are, the variation of u with respect to y is what we are after. So and the delta is the boundary layer thickness, that is the length from here to the edge of the boundary layer, and this can be defined as u is equal to 0.99 times of u infinity. Now, there can be two cases. Case number one, where the uniform outer flow, that is the flow which is coming from here and which is outside the boundary layer, is basically constant. That is, u is not a function of x. So, so u infinity is not a function of x. That means, so this type of flow, since it is not a function of x, that means at all x stations, u should be constant, should be same, and this can only happen if the pressure gradient on the plate is basically zero in x direction. So this is called as the zero pressure gradient boundary layer or ZPG boundary layer. Now there is a case 2 also, but we will discuss slightly later, where u is not a function of x. So for this case, the governing equation, which is the continuity equation, is given by is the same as the other case, as the general case. The momentum equation slightly varies, which is like this. This is u del u by del x. So if you if I say that there is no variation of u infinity, that means du infinity by dx becomes 0. So this gradient on the in the RHS of the first term of the RHS right hand side is basically 0. So therefore it becomes the continuity equation, becomes the momentum equation becomes u del u by del x plus v times of del u by del y. And the boundary conditions are the same, that is the u uh, 0 is at the wall, u and v both are 0. As you go outside the wall, outside the boundary layer, u goes to infinity, u becomes equal to u naught, since it is just u infinity is u naught. And the gradients at y is equal to 0 is 0, second order gradients. Now, the easiest solution to solve a steady boundary layer is by introducing the viscosity. Is introducing the stream function formulation. And in the stream function formulation, we express, in second year, you have already known this stream function to be continuity satisfying. So the first equation, so here, if you see, there are two governing equations. One is the continuity equation and the other is the momentum equation. So by choosing the stream function formulation, what we are doing is we are forcing the flow system to be continuity satisfying. So if I define u is equal to del psi by del y and v is equal to del psi by minus times of del psi by del x, and substitute this in the boundary layer equation, I get this third order partial differential equation in terms of stream function and x and y. Now we introduced a similarity solution. So one of the methods to solve is the similarity solution. Now this is because that people realized that as you go along the boundary layer, as you go in the x direction, move in the x direction, the velocity profile only stretches in x and y, and this is very easily shown with this help of this animation, which I'm going to show you now. If you see this, so it is only stretching. So y coordinate is stretching and x coordinate is remains same, and u value of u infinity is stretching. So the structure of the u versus y, the variation of the structure of u versus y remains same. So this is only possible. Sorry, yeah. And if you go into another slide, next slide, and that, yeah, now here I am showing you that at all these three uh, stations, there is a velocity profile. It has the same structure, and they basically collapse. So if we are able to define a variable which can make these profiles collapse at each other, then this variable is called as a similarity variable, and when we use this kind of a variable, uh, to solve the function, so to solve the flow, then this is called as the similarity solution. So here, as you see that at for any two stations, u is equal to x1 and at x1 and y1, u velocities are equal. So where y1 over g of x1 and y2 over g of x2 are basically same. So the eta variables are same. So then u becomes of the form f of eta, and where eta is y by gx. Now gx is called the similarity variable. So if you see over here, if you see over here, yeah. So gx is called a scaling function, and you have this kind of a variable which I have already explained to you in the graphics in the animation. So psi will then therefore become equal to u naught g times of f of x, f of eta, f of some function of y by gx. So if we are able to define or ascertain what is the value of g scaling variable, then we can use this formulation further. So we will be using this. So let me get rid of this animation. Now it is not needed. Yeah. So now before simplifying, let's calculate what is del psi by del y. So assuming that psi we can calculate the del psi over del y as this. Now since you can see that we get the same u naught, u is equal to, since u is equal to del psi by del y, we get u naught times of f of eta. Now f of eta is only a function of eta, where eta is y by gx. So it is basically, you can see that u becomes a function of eta. So this is what the premise of the similarity solution was there. Now we calculate these terms del psi by del x and del 2 psi by del x, del x del y, and del 2 psi by del x del y square, and these come out to be these terms, and you can easily do the calculus, and you can derive these terms. Now substituting this in the original equation of third order equation, we substitute it over here and we get this equation. Now if I collect the term and simplify, I get basically this. So if so that means if you can see that the first term on the left hand side is function of x, and the second term on the left hand side, which is f eta into f double prime eta, and the RHS are both function of eta only. Now, since the solution is in terms of f of eta, it is only possible if the LHS, first term on the LHS, is is independent of x. So that means let us call that value to be x square, and this is only possible. And it see, if it is a self-similar solution, that is the similarity solution is a self-similar solution. That means at all x, the solution is repeating itself. This is only possible if the solution is independent of x. So therefore, the governing equation, since the solution is independent of x, the governing equation should also be independent of x. So therefore, the only dependency on the governing in the governing equation on x is the left hand side first term. So therefore, they put this term as a constant term k square, and if I do it like this, then uh, in terms of k, I can evaluate what is the function gx, that is the scaling solution. You can put gx value to be any value. Now, the solution can be the simplest variable, since it's a independent of it's a just independent value. So it can be 1, 2, 3, 4, anything. This easiest equation is easiest variable, easiest value is 1. But Blasius used the value of 2, root 2, yeah, 2, k square equal to 2. So k becomes equal to root 2 in his customary. So Blasius was the first person, first student of Prandtl, and Prandtl was the originator of the boundary layer theory, and he first solved this on a flat plate, and this basically gave a lot of easy solutions, lot of easy things. So the governing equation becomes f triple prime k square. Now if you choose 1, then you can choose 1. You can choose 1 over 2 as the Blasius did, and you can simulate this. So the boundary conditions, but the boundary condition doesn't change. The value of boundary condition don't change. So now since this above equation is still a nonlinear equation, so we will use the RK Ridge-Kutta method for solving this. So f triple prime plus f times of f double prime, where eta is this, boundary conditions are these. Now solving this we are going to use RK method. So how to construct the system of equation for RK? So let us calculate, assume that y1 is equal to f, then y2 is equal to f dash, that is dy y1 over d eta. So this is again the IVP constructed. So one IVP will be, as you can see, the corresponding IVPs will be dy y1 by d eta is equal to y2. Again, similarly, y3 is equal to f double prime. So dy y2 by d eta is equal to y3. So here it is the same equation, IVP. Dy2 over d eta is equal to y3, and this final equation of f over f double prime, so dy 3 over d eta is basically f triple prime is equal to minus times of f. So this comes from the governing equation. Now for solving this, you require basically the initial conditions of y1, y2 and y3. But so if you require y1, conditions of y1, that is means you require function value f value of at 0. If you require initial condition for y2, so then f prime value of 0, and if you require dy 3, then you require f double prime value at 0. Now, as we know that u and v are 0, so from u and v we can calculate that at the y is equal to 0, is u and v are 0 because of the no slip boundary condition. So then u and v, that these two boundary conditions forces that f at 0 and f prime at 0 are 0. So they are known, but the value of f double prime, uh, f double prime at 0 is not known. So uh, so we guesses the value of f double prime such that f double prime value such that it becomes so such that f prime at infinity becomes equal to 1. So for numerical calculations, eta can be taken as infinitely large. So you can simulate into any value. So when we ran this RK method code, we obtained that f double prime at 0 is becomes equal to 0.4696, and this yields basically f prime of if eta equal to 1 for large eta. Now this can be, the table over here shows you this. So eta, f and f prime and f double prime. So we guess the value of f double prime such that it becomes 0. So you can use this is called the shooting method, and you use shooting method in combination with the RK method, initial value problem by the RK method, and you obtain the solution. So you can see that f when eta is equal to 3.5, this is f double f dash becomes 0.99289. So this is f dash. So if you remember the definition of u, so u becomes, u is equal to u. So if you remember the definition of u, then you can go back from here. So here, so you can see that u is basically equal to u naught times of f prime eta. So u over u naught is equal to f prime of eta. So from this definition of u, you know that 0.99 value, so that means 3.5 is the eta value which corresponds to the 3.5 value corresponds to the 0.99 times of u infinity. So this is the equation. From here you can calculate that delta 99% delta is equal to 3.5 times of, so 2 times of mu naught. So we are just invoking the definition of eta, and from here I can calculate that delta by x is equal to 5.0 times of Rex. Now if I calculate the shear stress, which is shown over here, so this comes out to be this value, and if I non-dimensionalize this shear stress, I get the variation of CF, that is the screen friction coefficient, with respect to Rex, which is again inversely proportional with respect to power half. Like I can, for an engineer, normally we know we want to calculate the drag values and the force which is applied on the system. So drag per unit length is basically 0 to L TWX dx, and CD is equal to drag by this length. So it calculates over here finally. So 1.328 times of REL raised to the power half. Okay. So this basically summarizes this part. So you can see that from this solution methodology, we were able to get the drag, estimate for the drag coefficient, and which was not accurate before this solution. Now, if I for the case 2 with a non-uniform outflow, again the continuity equation is written same, but the momentum equation where we put du infinity by dx to be 0, which is not possible now. So we have retained this term, and rest are similar. Now again the similarity solution, methodology of solution will be same. So we will again introduce the similarity solution. But here the difference is this: we introduce the station also. So if you will remember the first solution over here, we do not. So if we see the first solution which we showed in the case 1, uh, so the case 1 solution where we introduce the similarity variable. So there you can see that so we have not since x variation of the pressure gradient was not present, since x variation of the pressure gradient was not present, so we do not use the yeah, so similarity variable is similarly written. So yeah, from here u at x1 and u at x2 is equal. So and then we put a y condition also. Okay, so it's the same methodology which we are using again for the x gradient, but here the variation is that u by u naught, which is the function of x. U naught is, since u naught is a function of x, so we basically put it a that u by u1 u naught, which is function of x1, and u by u naught u x2, which is function of x again, they should be equal. So again, this can be true for the first case also, where u infinity was since it was constant, so then denominator cancels out, so the variation doesn't matter. But here, since the denominator has a variable x1 and x2, so therefore the denominators vary. So therefore the possible solution of the should be of the form u by ux should be equal to some function of y by gx. So again, the same thing, gx is the scaling function, eta is the similarity variable, and again we will use the same similarity stream function formulation, and we will assume that the form of psi to be u. There we did not put the variation of x, but here we will put this variation of x. So u gx and multiplied by f of y by gx. Therefore, so psi is equal to ux gx into f of eta, where eta is we defined as the y by gx. So again, we will let's calculate u. So as u by ux is some function of eta, where eta is only, so the RHS here is only the function of eta. So this is the what we desire, and so now we will calculate v here like this. V comes out like over here. So I have deliberately removed a g as a function of x, as only written as g, but it is just easy for easy writing. So again, del u by del x is some function of this u times of f double prime. So it is not written a function of eta, but it is basically a function of eta. So minus y by g square of g. So this is what we get. Substituting this in the momentum boundary layer, we get this kind of a relationship. Now you can see that there are two terms, u by u naught times of g into g prime plus u prime g square over mu naught. So now the second term in the bracket of the nonlinear term is basically the same. So therefore, if I put this term and this term both both these terms to be independent of x, then the self-similar summation can be obtained. So let us put first term as k1 and the second term as k2. So therefore, if we also get this 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 ratio, if we just divide these two terms, we get that ratio of u by u prime and g prime by g is equals to k1 over k. So k, which we can term as k. So from here we can safely say that if ln, so if we integrate by using this k, so both g and u are proportional to the log of g and u are proportional to each other. Now, as a special case, if just to check that, you can find that this comes at equal to the exactly the case 1. If I put ux equal to u naught, so therefore u prime, that is the du x by d equal to 0. So the solution of the similar is formed. Now the rest of the solution, I have not discussed the solution, the rest of the solution procedure. It basically is the same, and you can see in the White's book, Viscous Flow FM White book, or any book, you can see that. And it is normally the same procedure, so I'm not discussing the. So it comes as some error function of this. U is comes as some u naught times of error function of this. And of course also this is the zero pressure gradient boundary layer is the only thing which we discuss. And the approximate solution methodology, which we will discuss in the next class lecture, is also only based on the zero pressure gradient boundary layer. We do not compare the case of the pressure gradient boundary layers with this in this unit. So therefore, I will stop over here, and next class will be next lecture will be on the approximate solutions. Thank you.